The simplex algorithm requires a significant computational effort in linear algebra. In this video, we introduce a tool that is designed to simplify it. It is called the simplex tableau. When you look at the simplex algorithm, the main computational efforts are dedicated to calculate the three following quantities. First, we need to calculate the reduced cost in order to identify a descent basic direction. Then we need to calculate the entries of the current iterate for the basic variables, which is b minus 1b. And the calculation of the basic direction itself involves b minus 1 times the column of A. So if you look at these three quantities, they always involve the multiplication of the matrix b minus 1 with either a column of A or with the vector b. The idea of the tableau is that instead of calculating this product each time we need it, well, let's store it explicitly. So we will store b minus 1a, which is a matrix, and b minus 1b instead of storing a and b. And therefore, we'll have a direct access to the quantities that we need for the algorithm. So here is the definition of the tableau. First thing, let's define the dimension of this tableau. So remember that A is a metric which is m times n. B is the basic metric which is m times m. The vector b is a vector, so it has m rows for one column, and the vector c has n rows for one column. So it means that the first part of the tableau has m rows, and the second part is one row. In terms of the column, the left part of the tableau has n columns, as the matrix A, and the last column is just one column. We have basically the matrix B minus 1a, which takes the major part of the tableau, and we have one additional column and one additional line. Now let's relate these quantities with the basic feasible solution. Let's call it x tilde. So this is the basic feasible solution corresponding to this tableau. In this case, we know that the basic part of x tilde b is equal to b minus 1b, which is exactly this. This column here in the top part contains the value of the basic variables. Let's calculate now the objective function. The objective function c transpose x. Well, we know that all the non-basic variables are 0. So this is equal to cb transpose xb, right? We can ignore all the non-basic variables. And I put the tilde to emphasize the fact that I'm computing it for this feasible solution. And now I know the value of x tilde b. So this is equal to cb transpose b minus 1b. And actually, this is this quantity here, except for the sign. Therefore, this cell here, so this is in the additional column and the additional row, this cell contains the value of the objective function at x tilde, but we have to change the sign. And now when you look at the left part of the tableau, well, what you have here, each column here is b minus 1 times the corresponding column of A, and the last row contains the reduced cost for each of the variables. This is the interpretation of the tableau. Let's summarize this. Each column for the left part corresponds to one variable, from 1 to n. Each row of the top part corresponds to a basic variable, from j1 to jm. The last row on the left part contains the reduced cost, and on the right part contains the value of the objective function, where the sign is changed. Now we will exploit the fact that when you multiply b minus 1 times one column of A, if this column happens to be corresponding to a basic variable, well, then we obtain a column of the identity matrix, as we will illustrate in the example, next slide. So this column of the identity matrix for variable I, which is in the basis, will contain all 0 and 1, 1. Actually, we know that the reduced cost for variables that are in the basis is 0. So we have really a 0 everywhere except at that point. This is very useful because this will help us to identify which row is associated with this variable I. And remember, each row corresponds to a basic variable, and to make the link between the column, which contains all the variables, and the row, this is how we will do it. We will consider this vector of zeros and 1, 1, and the position of the 1 will tell us which row corresponds to this basic variable. Well, let's do it on an example. So I use an example here where I have 4 variables and 2 constraints. So this is the matrix of the constraint, which is 2 by 4. This is the vector B, and this is the vector C. Now I decide to select in the basis variable x2 and variable x4. I take these 2 columns and I form the basic matrix B. And I can calculate B minus 1. With this information, I can build the tableau. So the first column here on the top will be the multiplication of B minus 1 with the first column of the matrix, and we'll obtain 1, 2. Now if you calculate the multiplication of B minus 1 and the second column of the matrix, we will obtain, as discussed before, the column of the identity matrix. So we have a 0 everywhere, except here where we have a 1. So therefore, this row will correspond to the basic variable x2. And actually, we can do the same for the second basic variable x4, which has exactly the same structure. We have 0 everywhere, except here where we have a 1. This identifies the row corresponding to x4. If you look at the last row here, it contains the reduced cost. As discussed, the reduced cost for the variable that are in the basis are 0. And the other reduced cost, the one for the non-basic variable x1 and the one for the non-basic variable x3, we are positive. So actually this tableau corresponds to an optimal solution of the problem. All reduced costs are positive. What is this optimal solution? Well, we need to calculate the value of x1, x2, x3, and x4. x1 is out of the basis, so its value is 0. x2 is in the basis. Where do I find its value? Well, we have this part of the tableau here, which contains b minus 1b, which is the value of the basic variables. And we know from this relationship that this row here corresponds to x2, and this row corresponds to x4. Therefore, x2 is equal to 1. x3 is out of the basis, so its value is 0. And x4 is in the basis, and its value is here. It's equal to 2. And now what is the value of the objective function at this solution? Well, it is equal to this quantity where the sign is changed. So it's equal to minus 2. And you can verify that minus 2 is the result of the inner product between the vector c and the vector x. We have 0 times minus 1, plus 1 times minus 2, which is minus 2, plus 0 times 0, plus 0 times 2. Let's consider step by step each of the quantities that are needed by the simplex algorithm. We need the reduced cost in order to check if the basic directions are descent directions. These reduced costs can be found directly in the tableau here. We are just there, we just need to read them. There is nothing to calculate if we have a tableau. Then we need a basic direction. The basic direction, at least the basic part of the basic direction, is given by minus b minus 1 AP. Well, b minus 1 AP can be found directly in this part of the tableau. So we just have to keep in mind that the sign is changed. So what we read in the tableau is minus dB. Then we need to calculate the alpha I. Alpha I is the ratio between xb and minus dB. xb is found here. So the values of the basic variables is found in the last column of the tableau. And minus dB, what is found here, as we have identified before. So the calculation of alpha is really simple. You take one value here, and you divide by the value here corresponding to column P. And you do it for all entries of this column which are positive, which means that the corresponding values of the direction are negative. Then the solution itself, well, we know that the value of the non-basic variables are 0, and the value of the basic variables can be read directly here. And as we have discussed previously, the value of the objective function can be found here. We just need to keep in mind that the sign must be changed. Actually, the reason why we keep a minus here will be for convenience afterwards, so that we maintain the same form of the equation. If you look at on the left and on the right, it's all minus CB transpose B minus 1 times a vector. And here we have the same minus CB transpose B minus 1 times a vector. This is why we have this minus here, and we need to keep this in mind to calculate the value of the objective function. When you have a tableau, one iteration of the simplex algorithm is very easy. Actually, there is almost no calculation to perform anymore. You simply read the information in the tableau to decide which variable is out of the basis and will enter it, and which variable will leave the basis. But we are left with two difficulties that we'll have to deal with. First is that how do we prepare the next iteration? How do we calculate the tableau that will be valid for the next iteration? And the second one, how do we calculate the very first vertex of the algorithm and the associated tableau? In order to simplify the simplex algorithm, we use a tool called the simplex tableau. The idea is to store information instead of calculating them. The choice of the variable that will enter the basis is done by looking at the last row that contains the reduced cost and taking one which corresponds to a negative value. The choice of the variable that will leave the basis is done by calculating the alphas, the ratios of the value of x, which are read in the last column, divided by the value of minus dB, which are read in the column of the tableau corresponding to the non-basic variable. The smallest of these alpha identifies the row of the variable that will leave the basis. So this is very simple. Now we are faced with two difficulties that we will deal with in the next two videos: preparing the tableau for the next iteration and finding the first tableau of the algorithm.